Golden Iris Productions presents The Speed of Light by Mark F. Dennis, From Early Thought to Einstein's Relativity.
Introduction. For most of human history, no one knew whether light traveled at a speed at all. It appeared to arrive instantly, illuminating space faster than any motion could be perceived. Because of this, early thinkers struggled to even define the problem. Yet, over time, a simple question, does light take time to travel, became one of the most important questions in science. Answering it would require astronomy, precise experimentation, and eventually a complete rethinking of space and time itself. In this presentation, we'll follow the history of how the speed of light was discovered, measured, and understood, leading ultimately to Einstein's theory of relativity.
Ancient and philosophical views of light. In the ancient world, science and philosophy were not separate disciplines. The nature of light was discussed primarily through reasoning rather than experiment. Aristotle argued that light did not travel at all, that it was a state of illumination that appeared instantaneously. Because no delay could be detected by human senses, this view seemed reasonable and became widely accepted. However, some philosophers disagreed. Empedocles, writing in the 5th century BC, suggested that light must travel through space and therefore must take time, even if that time was extremely short. Without instruments or accurate clocks, there was no way to test these ideas. For centuries, the question remained unanswered. Galileo's attempt to measure light. The first attempt to measure the speed of light experimentally came in the early 17th century, led by Galileo Galilei. Galileo proposed a simple experiment. 2 observers would stand on distant hilltops, each holding a lantern. One observer would uncover their lantern, and the second would uncover theirs as soon as the light was seen. Galileo hoped to measure the time delay. Despite careful planning, the experiment failed. Any delay was far smaller than human reaction time. Galileo concluded that if light had a finite speed, it was extraordinarily fast, far beyond what could be measured on Earth using this method. Ole Rømer and the first true measurement. The breakthrough came from astronomy rather than laboratory experiments. In 1676, Danish astronomer Ole Rømer studied the motion of Io, a moon of Jupiter. He noticed that the timing of Io's eclipses varied depending on the distance between Earth and Jupiter. When Earth was moving away from Jupiter, the eclipses occurred later than predicted. When Earth was moving closer, they occurred earlier. Rømer realized the explanation was simple but profound. Light takes time to travel. The changing distance between Earth and Jupiter caused measurable delays in the arrival of light. For the first time in history, light was shown to have a finite speed.
Increasing precision, 1700s, 1800s. Following Rømer's discovery, scientists worked to measure the speed of light more accurately. In the 18th century, James Bradley used stellar aberration, a slight shift in the apparent position of stars, to estimate light speed. In the 19th century, laboratory experiments became possible. Hippolyte Fizeau used a rotating toothed wheel, while Léon Foucault refined the method using rotating mirrors. By the mid-1800s, the speed of light had been measured with remarkable precision, close to 300,000 kilometers per second. At this point, the speed of light appeared to be just another physical constant, but a deeper problem remained. Light as a wave and the aether. Light exhibits wave-like behavior, and during the 19th century, physicists believed that all waves required a medium. Sound requires air, water waves require water. By analogy, light was assumed to travel through an invisible substance known as the luminiferous aether. This aether was thought to fill all of space and provide a reference frame for motion. If Earth were moving through the aether, then the speed of light should vary depending on direction, just as sound behaves differently when moving through wind. Experiments were designed to measure this effect.
The Michelson-Morley experiment. In 1887, Albert Michelson and Edward Morley conducted the most famous of these experiments. Using a highly sensitive interferometer, they attempted to detect changes in the speed of light caused by Earth's motion through the aether. The result was unexpected. No variation was detected. Light travelled at the same speed in all directions. This result was deeply troubling for classical physics. Either the aether behaved in very strange ways, or it did not exist at all. Einstein and special relativity. In 1905, Albert Einstein offered a radically different interpretation. Rather than trying to explain the null result through increasingly complex assumptions, Einstein accepted it as a fundamental property of nature. He proposed two principles. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion. These assumptions led to surprising conclusions. Time is not absolute. Lengths depend on motion. Events that appear simultaneous to one observer may not be simultaneous to another. The speed of light was no longer just a measured quantity. It became a defining feature of space-time itself.
Why the speed of light matters. In Einstein's framework, the speed of light represents the maximum speed at which information and causality can travel. Nothing can carry cause and effect faster than light without violating the structure of space-time. Modern technologies depend on this understanding. GPS satellites require relativistic corrections to maintain accuracy. Particle accelerators operate near light speed. Cosmology uses the constant speed of light to interpret the universe's history. The speed of light is now understood as a fundamental limit built into nature. Conclusion. The discovery of the speed of light was not a single event, but a centuries-long process. It began as a philosophical question, became an experimental challenge, and ultimately forced a complete transformation of physics. By understanding how scientists uncovered the speed of light, we also see how science progresses, not by certainty, but by careful questioning, measurement, and the willingness to revise deeply held assumptions. The speed of light is more than a number. It is a cornerstone of modern physics and a guide to how the universe works.